In section 14.2, I'm going to discuss how forces can contribute to a change in momentum for an object or system and how we can quantify that with impulse. To start out, let's consider an object that's being pushed by some net force. So let's give our object mass m, and let's say that it is being acted on by some net force. We'll just picture that net force as acting to the right. Now, we should recall that accelerations are caused by net forces. If there is a net force, there's automatically an associated acceleration. Accelerations are associated with a change in velocity. And it's the rate of change in velocity that is the acceleration. And we need to be a little bit careful here because acceleration is direction dependent. Force is direction dependent. Velocity is direction dependent. They are all vector quantities. And so if we have an object that is moving in some way, this net force is going to cause its velocity to change. And recall that the momentum of an object is in the direction of its velocity. So if the velocity changes, that means we're going to have an associated change in momentum. Now, if I just take this part of the equation that we're working with, we don't really care about the acceleration here. If I do a cross multiplication, we're going to end up with a useful result. We end up getting on the left-hand side the net force times the time. Now, this is the time for which this net force has been acting on the object. And that's going to equal the mass of the object times the object's change in velocity. And again, we have to be careful for the direction-dependent vector quantities. And what we have here is on each side of the equation is going to represent an important quantity. So on our left-hand side, this is what we refer to as an impulse. And an impulse is represented, don't ask me why we picked this letter, but we represent it with a capital letter J. If there is an impulse that occurs for an object, that object is going to have a change in velocity. And if you multiply the change in velocity, well, then you end up getting the change in momentum. And since these are equal, the momentum, the impulse is equal to that change in momentum. And this is what we would call the momentum impulse theorem, that when a force acts for some amount of time, it will cause an associated change in the momentum of an object. As discussed, external forces that generate a net force can cause the momentum of a system to change. And we refer to this change in the object's momentum as impulse, and we use a capital letter J to represent that. And here you see a big long equation. We've got 4 parts to this, and they're all representing the same quantity. So J represents impulse, and you can find impulse by multiplying the force acting on the object or the system, the net force, times the time for which that net force has been acting. That impulse will result in a change in the object's momentum, and that we can find the change in the object's momentum by multiplying the mass times its change in velocity. Notice that everything with the arrow over it is a vector quantity. The direction is really important. The units for impulse are going to be the same units as momentum because impulse represents a change in the momentum. So if you're asked to calculate impulse, you will be calculating it in kilogram meters per second. Now for some examples. A baseball has a mass of 150 grams. We should immediately take this and convert it to kilograms. That's giving us the mass. And converting this to kilograms, we'll divide by 1,000. There are 1,000 grams in a kilogram, so 150 grams is 0.150 kilograms. Let's consider a 35 meter per second pitch. That's about 78 miles an hour. What is the impulse experienced by the ball if it is caught by the catcher? So to find the impulse is equal to the change in momentum for the ball. And the change in momentum would be its final momentum minus its initial momentum. Now, if the catcher brings the ball to rest when he catches it, that means that the final momentum is going to be 0. So the impulse is just going to be equal and opposite to the initial momentum. The initial momentum can be found by multiplying the mass times the initial velocity. We have the value for the mass, that's 0.150 kilograms, and we have the initial speed. The initial speed was given as 35 meters per second, and when we multiply those two together, we end up getting negative 5.25 kilogram meters per second. Now, what's up with this negative sign? So that comes because this negative sign here, and that's really just telling us that if we consider the initial velocity to be positive, so we've got our baseball moving towards the catcher, and I had put that 35 meters per second in as a positive number. That's indicating that the towards the catcher direction, where the ball was initially moving, is my positive direction. And this should make sense. The impulse is in the same direction as the force. The catcher is going to have to apply a force to the baseball in the negative direction. So that's what this negative sign is indicating. It is indicating direction. Okay, so for part B, what average force does the catcher exert on the ball? So impulse can also be found by taking the net force and multiplying it by the time. So we can rearrange this for force by taking the impulse and dividing it by the time. We had the impulse as negative 5.25 kilogram meters per second. And if we divide this by the time that was given in seconds, we will get 105. And the units are going to work out to be kilograms times meters per second squared, right? We'll have seconds squared. Well, that's mass times a unit of acceleration. That gives us a unit of force, the Newton. All right, and part B. What is the impulse if the ball is hit by a batter as it leaves moving back towards the pitcher at 50 meters per second? So, there's a common mistake alert here. This is something that students will incorrectly do every single year. And I'm going to point out the mistake after making it. So most students will say, all right, I know how to calculate impulse. Impulse is just the change in the momentum. And the change in the momentum is the mass times the change in velocity. Well, we knew the mass. That mass was the converted 0.15 kilograms. And I know how to find a change in something. I just take the final value minus the initial value. Well, the final value is 50. And before the batter hits it, it was moving at 35. So, I can calculate the impulse. That works out to be 2.25 kilogram meters per second. Now, that should be suspect. All right, it's suspect because look, this impulse, this is less than the 5.25 kilogram meters per second that we found for the catcher to catch the ball. It should be harder for a batter to hit the ball than it is for the catcher to catch the ball. Right? There's a bigger change in momentum. Now, here was the mistake, and it's the mistake students make every year because impulse, momentum, velocity are vector quantities. They depend on direction. So if we picture the ball as coming in with an initial velocity this way of 35 and leaving with a final velocity in the opposite direction, we have to make one of them negative. Okay, so I'm going to make the final velocity negative. And when you make that correction, you get the correct value for the impulse as negative 12.75 kilogram meters per second. The negative sign indicates that the change in the momentum was in the negative direction. That makes sense. The batter was exerting a force in this direction. Momentum and impulse are always in the same direction, which would be opposite the direction that the ball was moving initially. Okay, in this example, we have two passengers, both with the same mass, riding in a car when the car hits the tree and is brought to a stop. Passenger A wasn't wearing a seatbelt and is stopped in some amount of time. Passenger B is wearing his seatbelt and is brought to a rest in a time 3t. That is what a safety belt does. A safety belt will bring a passenger to rest in a longer amount of time because it starts stopping them. It starts applying a force to them earlier. And so that is what is going to keep the passengers safe. So, part A, which passenger experiences the larger impulse? Well, impulse is the change in the momentum. And the change in the momentum is the mass times the change in velocity. Now, both passengers have the same mass. Both passengers started with the same velocity and they ended with the same velocity, so they both have the same change in velocity. So if they have the same mass, the same change in velocity, that means they are going to experience the same impulse. The safety belt does not affect the impulse because the impulse is the change in the momentum. But which one will experience the larger force? Well, they experience the same impulse, but they do not experience the same force. Impulse is force times time. Notice that force and time are multiplying to equal the impulse. Well, if two things multiply together to equal the same thing, that should tell us that force is inversely proportional to time. The faster this deceleration occurs, that will require a larger force. So, passenger B gets brought to rest over 3 times as much time. Therefore, passenger B will experience 1/3 less the force that passenger A does. So, we can write this as a nice, concise statement. Passenger A experiences 3 times the force as does passenger B. Okay? Why? Because this force acts over 1/3 the time. Okay? And this is the whole idea behind everything safety-wise. Safety belts, airbags, a helmet, the catcher's mitt from the last example. All of those are looking at this idea that for the same change in momentum, the force is inversely proportional to the time. So for the same impulse, you can have a force times a large time. This was passenger B. Or you could have a large force exerted over a very short time. And this is what happened to passenger A. The safety devices in your car want this to happen, and we don't want this to happen because it is not the impulse that causes injury, it is the force.